If you recall last time, we introduced the coordinate systems in 3D, and we introduced the distance formula, and we introduced, how to calculate distances between geometric objects, such as a point and the coordinate planes, and also distances between spheres. We learned what the equation of a sphere was. So I thought today maybe let's just do a quick warm up with these ideas. Consider the following equation. So let's say show that the object given by 2x squared plus 12x plus 2y squared plus 2z squared plus 6z is equal to 4. All right, show that the solutions to this equation in R3 is a sphere. And furthermore, let's try and find its center and radius. So let me maybe give you a couple minutes to think through this. So recall from last time, maybe you could flip to your notes from last time, that there's a very standard formula for a sphere. So recall a sphere centered at ABC of radius r is given by the following equation, x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. All right, so something very similar to a circle, the equation of a circle in 2 dimensions, but you have one more variable that you're squaring in a sense. All right, so does someone want to volunteer in chat maybe how you might find the center radius of this equation here? Maybe don't type everything out if you don't want to, or if you're still working on it, but what's a general strategy we might do? So, right, so the answer is to complete the square like we did last time, right? So if you recall, last class, we started with an example where we were in polar coordinates in 2 dimensions, and we were able to convert that, a particular polar curve into Cartesian, and then we showed that it was an off-center circle, in essence, by completing the square. In this scenario, we also want to complete the square in these different variables to reduce it to the standard form here, all right? So let's take a look at how this is done. So this is complete the square to find the standard form, the standard equation for a sphere. Yes, so let's walk through how we complete the square here. So first, let's divide everything by 2 here. All right, because if you satisfy this equation, divide out both sides by 2, you're going to satisfy the new equation anyways, and just simplify its coefficients. So divide by 2. So first, divide by 2 gets you the following equation: x squared plus 6x plus y squared plus z squared plus 3z is equal to 2. Right? That's just dividing both sides of these by 2, and you're allowed to do that. You're really not changing the equation you're looking at. And now let's isolate each of these variables and try and complete the square, right? So remember, our goal is to turn something like this into something like this, right? Because once we get this in this form, it's very easy to figure out where the center is and where what the radius is. And Eva, yes, that's right. We want exactly this form. So completing the square, what I mean by completing the square is you have something that looks like x. Let's just look at x, right? X squared plus 6x is not of the form x minus a all squared. So you want to basically transform this here in the into something that looks like x plus or minus a scalar a, plus or minus a number a, all squared, and then you're probably going to have to add or subtract another number just to make sure that this looks like this. So what do I mean here? Well, think back to some maybe algebra pre-calc. X squared plus 6x becomes the following. So x squared plus 6x, you complete the square. This is x plus, if I do x plus 3 all squared, if I expand this out, this is going to be x squared plus 3x plus 3x again, which gets me 6x, and then plus 9. But there's no plus 9 on this left-hand side, so I got to subtract off a 9, right? So as a rule, if you recall completing the square, the coefficient of the linear term in x, the coefficient here is 2 times what this constant has to be. That's the rule. So you see there's a 6 here, you divide it by 2, and you get 3. So then you have to subtract off the extra bit that you get from here that does not appear in your original equation. All right, so y squared stays the same because y squared is already in the form that we want, so this gets unchanged. Now, does someone want to give me how do I complete the square for z squared plus 3z? Remember, the coefficient of the linear term here has to be, is 2 times the coefficient that appears in the interior part of the bracket that you're squaring, Right, so it should be z plus 3 halves, that's correct. So it's z plus 3 halves all squared, and you got to subtract off the extra, which is 3 halves squared, and that's 9/4. So you subtract off 9/4 to get what you wanted. All right, so then you have these relations here, and so your equation now becomes, you want to substitute everything in. For x squared plus 6x, you now have x plus 3 squared minus 9. For y squared, that's still the same. And then for z squared plus 3z, you now have z plus 3 halves all squared minus 9/4. And that's equal to 2. So much closer, but not quite what we want yet. We have all these constants here. So let's move these constants to the right-hand side, right? So let's add 9 and add 9/4 to both sides. And so now we have x plus 3 squared plus y squared plus z plus 3 halves all squared equals, so it's 2 plus 9, right? So that's 11 plus 9/4. So what is that? That's like 44 plus 9, which is 53, right? So what is the center and radius here? Right, so it should be -3. Remember these things, there's a, you want to switch the signs in front of these in the equation, right? That's how the rule works. So it's -3, 0, and -3 halves. So center, -3, 0, -3 halves, and radius. Radius, you want to square root the number here, so that's root 3/4. Something to note here, just by the way, when you have something of this form here, you're going to complete the square, and what's always going to happen is you're going to have to subtract off some constants here, right? Because when you complete the square here, you're probably going to get a bit extra, and you need to end up subtracting numbers here on the left on this side of the equation, which means that you got to add numbers here. You should never fear that the number here is going to be negative. This number here is always going to be positive because you're always going to be adding stuff. And so your radius is always going to be the square root of something positive, which you're allowed to do. If you end up somehow taking a square root of a negative number, like somehow you complete this process and you have something negative here, then, sorry to say, what you started off with is probably not a sphere. And we'll get to more general surfaces later. But, if it's a sphere, you complete this process, it has to work out. Okay, let me do another example here, and then we'll look at another class of surfaces in three dimensions before we move on to vectors. So example, well, let me just recall last time. A point with coordinates x0, y0, z0 in R3 has a distance of the following, has a distance absolute x0 from the yz plane, has a distance y0 from absolute y0 from the xz plane, and it has a distance z0 from the xy plane, right? So the picture, let me recall, is the following. You have x, y, z coordinates here. You have a point here. Let's say that's your point P. Then you can project, right? How high off the ground P is. This distance here is absolute x0. No, that's not what it is. It's absolute z0, right? It's how high off the ground. If you imagine xy plane as being the ground, z equals 0. Then this is z0, absolute z0. And you can project it various different ways to get the distance, right? So over here, this is given to you by absolute x0, and then you have another distance here. How far you are off the xz plane. This is y0. Okay, now let's ask another question. So what is the distance, let's say, so what is the distance from P of, I guess, between P and, let's say, the following: the x-axis, B, the y-axis, and C, the z-axis. So maybe actually, because of this picture here, and it's easier probably to see the distance from the z-axis here, or maybe you don't have to contort your head as much. Let's focus on the answer to C first, or the question C. How far is this distance P with these coordinates, which means z0 here, with these coordinates? How far is this from the central axis here? But how might we do this? All right, so Ibrahim says square root x squared plus y squared. So that's a good candidate, right? So let's see how we might see this by some trig. So here's a strategy, right? If I look at P here, and I just cover up the z coordinate here. Let's suppose I ignore the z coordinate here and just look at P is equal x0, y0, something. Now, what z0 is just controls how high off the ground I am, right? In this vertical line that goes through P, in a sense. Geometrically, I hope visually the picture might be clear. There is a whole line of points vertically through P that have the exact same x naught and y naught coordinate. It's just the z component that varies, right? Z controls how high off the ground you are. P happens to be z naught, but there's a vertical line, maybe this dotted line in orange. That's vertical. Now the distance between P and the central z-axis is really the same thing as if you just look at the vertical line through P and see where it intersects the xy plane. That's at x naught, y naught, z equals 0, and measure the distance of that if you want the shadow of P on the xy plane with the central point here, in this case the origin, right, of 0, 0, and z is equal to 0, right? You basically translate this distance all the way down, all the way down, all the way down, and it's the same distance down here. I hope that's, hopefully visually a bit clear. So the strategy is measure the distance of the shadow, let's say of the xy shadow of P to the origin, right? So in this case, the shadow of P looks something like this. This is x naught, y naught, 0. And I also have a central distance here that I'm measuring. So this is the same distance as if I hadn't measured this. So what is the distance here? The distance is given by the square root of x naught squared plus y naught squared, right? Because the distance from x naught, y naught 0 to 0, 0, 0 is just, it's exactly what this is. All right, so someone want to volunteer what the distance of the x-axis is? Right, so in this case, from the x-axis, right, you just want to do y naught squared plus z naught squared. And for the y-axis, it's going to be x naught squared plus z naught squared. So here we are. Let me present to you one other, nice class of surfaces. So the following, what is the surface in 3 dimensions that satisfy the following equation: x squared plus x squared plus y squared is equal to r squared. Dumb question in a sense, because not a dumb question, but it's different than what you might expect immediately, right? Because in R2, this is a circle, but in R3, what is this? Right, so we have one guess, which is the surface of a cylinder. And what's the reasoning for this? Well, you can see here. Let's look at the example in C, right? What I have on the left-hand side here is essentially the square of this. It's saying I'm looking for the set of points x, y, and z such that x and y satisfy this equation. X squared plus y squared is equal to r squared for a given r squared, for a constant, let's say, r. So what is that? Well, in other words, I'm looking for the set of points in R3 such that its distance from the z-axis is constantly r, right? This is the distance squared from the z-axis, and this right-hand side is some constant. So I want the distance squared to be some constant, then its distance must be the square root of this constant. So I'm asking that this is the set of points P, whose distance to the z-axis is the square root of r squared, which is r. So this is what? This is a cylinder. I guess I'll specify. It's a circular cylinder of radius r, centered at 0, 0, 0, extending along z, right, vertically. So pick up, as a diagram, let's draw this. This is in x, y, z. I have a center here. I have, right, there's 0, 0, 0. I have a set of points here. Let's say this has radius r, and I'm looking at the cylinder here, right, extending vertically. It's an infinite vertical cylinder, right? Because every single point lying on the surface of this. So all these are surfaces, they're 2-dimensional shapes, right? This is like a rolled up sheet of paper, if you will. So every single point on the cylinder satisfies the fact that its distance from the central z-axis is at a fixed distance r. Okay, so Thomas asks a important question. Why are we assuming all values of z are in r? That's because I'm just asking, when I say what is a surface in R3 satisfying x squared plus y squared equals r squared? Well, every single point in R3 is described by x, y, and z. This is very, it's very important that I specify this equation. I'm looking for a surface in R3 satisfying this. If this were a surface in R2, then this is definitely just a circle, right? Because there is not even a z dimension to consider. But if I'm just looking for points that satisfy this in R3, well, then every single point has x, y, and z. I have absolutely no restriction what z has to be. Z could be -1, z could be a billion, and it never shows up in this equation. This equation only constrains what x and y values of P have to be. So z really is allowed to take any possible value. So does the cylinder have height? says Umer. Yeah. So the answer here is no. The answer is yes. There's height. The height is infinite. There is not any interval for z could be chosen in this case, because strictly speaking, the answer to this is really just an infinite cylinder. It goes up infinitely. It goes down infinitely. I didn't give you any restrictions for what z could be. If I had said what is the surface in R3 satisfying this equation with z greater than or equal to 0, then that would be the half cylinder, right? It includes the bottom portion here, or the circular portion here on the bottom at z equals 0, and it extends infinitely upwards, but not downwards. But without any other specification of what z is in this question that I posed, there is absolutely no reason for this cylinder to be constrained in any finite interval. So z is between minus infinity and plus infinity. All right, so this is an infinite cylinder up and down. There are generalizations of this, of course. You could move the cylinder if you tilt it somewhere else. If you want a cylinder that surrounds the y-axis at a certain radius, you can modify this, right? This becomes x squared plus z squared is equal to r squared, and you get a cylinder of radius r extending infinitely along the y dimension, centered at 0, 0, 0. And you can also move these around, but I think we'll look at how you can move these around a bit later when we do more general surfaces. So let's move on to vectors now, and let me try and motivate what vectors could do for us. One thing you'll notice is we have two classes of surfaces now. We've found how to describe spheres in R3, right, by this equation here, and we have circular cylinders in R3, right? So in a sense, these are somewhat very basic shapes. They all have some sort of symmetry, but they're pretty basic shapes, and we know how to describe them now in 3 dimensions. But you might be wondering, I mean, there are even more basic shapes than this that we haven't actually gotten to describe, right? A sheet of paper, for example, is a plane. That's what you call it, right? It's kind of like a copy of the XY plane, but it could be oriented in a certain way. It could be tilted in 3 dimensions, right? A sheet of paper you could hold at different angles, facing different directions. And we haven't really described how you would describe, how you would give this surface yet in 3 dimensions. So that's an awfully simple surface that we don't know how to describe quite yet. Perhaps even more concerning, we haven't really described what lines are, right? The first thing we saw in 2 dimensions was, back in high school, y equals mx plus b defines what a line is in 2 dimensions. We don't even have that yet in 3 dimensions. So we're going to try and solve that as soon as possible. And to do that, we need a vector, or the notion of a vector. Let me try and give you the informal definition, the geometric definition first, and we'll do a few visual computations with it. Then we'll do some actual more involved calculations. So what are vectors? These are arrows with both a magnitude and a direction. Visually, all right, I could draw an arrow like this. I'll call this arrow V with a little arrow on top. This is how you would handwrite abstractly what a vector is. And note that this arrow here has both a direction, is pointing this way, and it has a length, right? You could take a ruler to it and assign the length, for example. This is all very abstract. I know it's, I could draw another arrow here in purple, make it shorter, and I'll call this W. This is a different vector, right? It's pointing somewhat downwards, and it's of a slightly shorter length. Vectors are just arrows with both magnitude and direction. A very hand-wavy definition, but it is true. Why do we care about these? So there are 2 main motivations that we need to care about. The first thing is maybe geometric. How do we express planes and lines in R3, for example, right? And you'll see this, right? If I tell you, let's say a tourist comes across it, to Toronto and asks, which direction is the CN Tower, for example, right? Where's the viewing platform to the CN Tower? You don't say, okay, pretend you're the origin, the CN Tower, pretend Z is upwards and X is a certain direction, Y is a certain direction, and I'll give you, I'll express precisely where in coordinates the CN Tower, or the viewing platform of the CN Tower is, right? What you do is you take your hand and say over there, right? And what you're doing here is you're roughly assigning a direction, right? You point with your finger and you assign a direction to the lost tourist or whatever to give direction. So in a sense, this geometric motivation is very natural to consider what vectors are. right? In the real world, you really do a lot with vectors. You point in directions and you tell people that's where they are. You don't give them the equation of a line, some sort of weird algebraic equation, and say, follow this algebraic equation, and that'll get you there, right? You point. So in other words, straight lines you could think of just visually. We'll get to this. We'll get to this in more specificity later. But really, for a line in 3 dimensions, what you really need is just a direction, right? If I draw a little arrow here, then I can assign you a line that is going in that direction. The line that's going this direction is, it goes this way and it goes this way. This is a line that, this is L goes through, L is a line through in the direction of W, I guess. Let's call this U now, and let's say through a point P, right? So in essence, what we'll see later is, if you want to describe a line in 3 dimensions, something very intuitive that you might do is just say, okay, well, I want my line to go through a fixed point, right? So let's say some point P, but there are a lot of lines I could draw through a point P. What I really want is through this point, I want a line going through this point P in some direction, and I indicate a direction, and that indication of a direction is a vector. Now, how do I express planes in R3? Well, what I could say is, okay, well, I want to say which direction, if I were on an ant living on, say, a sheet of paper. So if I have a sheet of paper here, let's say instead of a sheet of paper like this, I want to indicate my sheet of paper is like this. You could say, if I'm an ant that's living on this sheet of paper, then I want to indicate that my direction of up is pointing this way, off the sheet of paper. So in other words, describing a plane is really an indication of a direction of which way is up. A plane is, I could indicate with another arrow. Let's say I'll do the same vector U as before, and I say, okay, well, a plane, I could just say that, let's say the plane, right? So let's say this is a plane pi containing a point P, right? Let's say I want to go through some point P, making right angles with the direction U. All right, in this case, this U is at right angles to this plane. All right, so the geometric motivation hopefully is pretty strong. Why we need to consider these objects. These are just arrows with both magnitude and direction. In this case, we've mostly focused on the fact that these have directions. If I have a direction, I could indicate to you both what a plane is associated to a direction just by taking right angles, and I could also indicate to you what lines are, right? Their lines are indicated by shooting off in a certain direction. So that's the geometrical motivation of vectors. Now, there's also a physical application of vectors. So the physical application, forces, velocities, accelerations. So velocities and accelerations of particles are all vectors. For example, right, let's say the gravitational force field, right, on Earth is roughly 9.8 newtons per kilogram downwards, right? Notice that I didn't just say 9.8 newtons per kilogram, it's 9.8 newtons per kilogram downwards, because gravity doesn't, float you upwards. 9.8, doesn't exert a force upwards. It always pulls you towards, towards the ground. So these forces always have assigned to it a direction. Now, when previous calculus classes, we've restricted ourselves to one dimension, right? So implicit in this, you could always, if you have a force in one dimension, you could really just describe it by being positive or negative. But as soon as you go up in 2 or more dimensions, then you have to find another way of describing which directions forces are. A force has a magnitude, but it also points in certain directions, right? So hopefully these are all good, motivations for you as to why forces are important, of why vectors are important. They model both geometries, and they also model what forces are. So, for example, gravity on Earth is approximately 9.8 newtons per kilogram downwards, right? So this is a direction, and you have to indicate it, otherwise it's not correct, right? 9.8, I just tell you gravity is 9.8, you have no idea what that means. Let's look at adding and subtracting vectors and things like that. All right, so let's look at operations on vectors. The most simple one is addition. So let me copy my 2 main vectors here. So addition just means that I want to add these together. So what I do is I get one vector here and I get another vector here, and I place the tail of one to the tip of the other. I could either do it this way or I could do it this way. I could either do it this way or I could do it this way, right? Adding v to the tail of v to the arrowhead of w. And these are all going to result in the following vector, which is this. All right, so visually you just place the tail of one to the tip of the other, and then you draw the resulting arrow formed by the old tail and the new arrowhead. All right, so this is the vector v plus w. And then there's scaling. Let's say if c is a constant, so it's a real number, then if I similarly take, let's say v here, and I scale it, then c times v is going to be a vector that points in the same direction as v, but has a different length. All right, so specifically what I'm saying is, let's say v has original length given to you by this. So this is my notation for the length of a vector. All right, it has 2 bars on each side and v in the middle. Sometimes you'll put 1 bar. It's a matter of convention. But let's say I have a vector v with some length here. Then the new vector with cv is the vector pointing the same direction as v, but it has a length given to you by the absolute value c. Well, okay, I should probably specify. Let's pretend it has new length cv if c is greater than 0, or it also has it's the vector given to you by reversing the direction of the arrow. So instead of pointing in this direction, you're now going the opposite direction. And this arrow has length absolute value, I guess, absolute value c v, but it points in opposite, so points opposite to v. So subtraction, let's now take a similar scenario here. So we had previously addition, and now we have subtraction of the arrow here. So how would I do this in this case? What is v minus w? Which direction is v minus w? Is it pointing upwards or downward, or roughly upwards or roughly downwards in this case? In this case, let's see, right? What happens is, if you look at this diagram, this schematic here, I could do the same thing, but now this is the same thing as if I took the same, but I've just added this to minus w. And if I add minus w to it, so what happens is I switch the sign of w, which is minus w. It has the same length as w, it just points in the opposite direction. I'm adding these two together. So once again, I add these tail to tip, roughly. So tail to tip, like so. And my resulting vector looks like this. All right, this is a vector v minus w. So the answer is up. Well, in this case, it's probably poorly drawn vectors. They're both kind of up, but this one's very up, if you could see. Another way you could do this is really you could just say the different, another way of doing this, which some of you might find better, is you could take, if you subtract w from v, you just put the tail of w to the tail of v, and then you look at the resulting arrow from w to v. All right, and this points the same direction. It's the same way of doing things. So once again, you can put the tail to tail and go from w to v. You just have to remember that you go from w to v and not v to w if you do that. So if you find that confusing, I would recommend visually imagining this instead. Let's see how we could actually do some calculations with vectors that are not just not caveman drawings. Okay, so just like we have coordinates for positions and in a point in R2, we could describe a point in R2 by two quantities, x and y. We want to find a way to actually quantify what a vector is. So we need coordinates to describe vectors. So what we do is you place the tail of the vector at the origin and describe the arrowhead using Cartesian coordinates. Right. So for example, take our vector v again. So our vector v is here. Then in 2D, I would put coordinates here, or use the coordinates here, and I would describe this. Let's say v has length a in the let's say it has length v1 in the x direction, and then it has length v2 in the y direction. Then in R2 is a two-dimensional vector. So if v is a two-dimensional vector, we can write v is equal to v1, v2 with angle brackets. These are what we call the components of v. All right, there's a component of a vector in the x direction and a component of the vector in the y direction. And we call these v1 and v2. These are components. We don't call them coordinates when they're a vector. We describe these in terms of components. Or you could also see it written as v1i with a little vertical arrow on top, a little hat on top, plus v2j, where ij are unit length vectors in the x and y directions, respectively. That's the case in 2 dimensions. So let's say if u is a 3-dimensional vector, we can write u is equal to u1, u2, u3, or you could also write this as u1i plus u2j plus u3k. All right, and now you have an extra term here where this is the unit vector in the in the z direction. All right, so in this case, let's say I have some vector u in 3 dimensions. Then in the 3 dimensions here, I draw my usual coordinate system, right? And I could describe this in terms of components, right? Just by projecting. So this length would be u1, or sorry, u3, and so forth. I have this dimension is going to be u1, and this dimension is going to be u2. Any questions on how we describe vectors in terms of components? Okay, so what's the length of a vector in this case? So let's say I have a vector of length in 3 dimensions of u1, u2, u3. What's the length? What's the magnitude of this arrow? U has magnitude, right, given to you by the distance formula. Once again, right, this is none other than in the usual 3-dimension coordinate system. You want to find the length of this hypotenuse, so you use the same formula, and you find the distance from the arrowhead to the tail, which is the origin. So this is magnitude. It's a positive square root of u1, u2, of u1 squared plus u2 squared plus u3 squared. And this is similar in 2 dimensions, right? In 2 dimensions, you only have 2 components to worry about. So there is just these first 2 terms. There's no third term here. You could also, I guess, in this class, we're exclusively focusing on 2 or 3 dimensions pretty much, but vectors can live in any number of dimensions. So in these cases, we only look at 2 and 3 dimensions. You have more dimensions. Let's say you have a 4-dimensional vector. Let's say you're doing general relativity, special relativity, anything. Space-time is 4-dimensional. So vectors in space-time are going to have a 4th component here, which you'll just append to the end of this. You could even have vectors of 1,000,000 components. These come up in statistical analyses all the time. There's something that we'll get to called the gradient vector, and this comes up in optimization problem. If you're, AI is all the hot stuff right now. So AI models, what they do is, the statistics behind how you train models is you want to minimize a certain error. To minimize a certain error, you need to compute a certain vector called the gradient. And this has to do with data entries, the data that you collect. And you have a lot of data with a lot of, components to the data, then this is going to be represented in your model by a vector of very high dimension. So you could have billions in this. But in this class, focus on 2-dimensional vectors and 3-dimensional vectors. Let me introduce to you some operations. So I guess let me say this. So vectors can live in any number of dimensions, but you can only add and subtract vectors of the same dimension. All right, that's just sort of how it works out. You can't have vectors living in 2 dimensions, 2 different dimensions, like they're living 2 completely separately different worlds. All right, they're different categories of things, so you can't really add those together. But if you're in the same dimension, let's say we're going to work exclusively in R3 for this illustration, but you could see how these operations generalize in higher numbers of dimensions. So if I have 2 operations for V with these components and W with these components, then it's very straightforward. V plus W is a vector where you just add component-wise, all right? In the X component, you had V1 and W1. Now the new resulting vector has component V1 plus W1. Then you have V2 plus W2, and then you have V3 plus W3. And similarly, you have subtraction is V1 minus W1, V2 minus W2, V3 minus W3. And let's say if C is a constant, then C times V is none other than the vector that results when you just multiply C component-wise. So V1 becomes, the X component V1 becomes CV1, V2 becomes CV2, and V3 becomes CV3. Nimrat has a good question. Can you multiply 2 vectors together? Yes. We'll get to that. Probably, let's see how much time we have. Perhaps not, maybe at the very end of this class, we'll look at one way to do so. But it requires some thinking, all right? But it's very important that we know how to multiply vectors together, and we'll get to that. If you put some thought into it, it's kind of hard geometrically to say what it means to multiply 2 vectors, right? So we have an interpretation for what CV means by our picture up top, right? If I have, let's say this for simplicity, if C is positive, then I take an arrow and I scale it by c, that just means I get the arrow in the same direction, but I just lengthen it, right? I scale the magnitude of it by c. Now, if c were some sort of vector, then I'd have to put some real clear thought into what it means to multiply, right? Axe says, yes, we do dot and cross product. That's coming up almost immediately after this. So the dot and cross product are the multiplication operations that we're going to look at vectors. They take some interpretation, and we'll get to that very soon. But hopefully, let's keep things simple for now. These are the very basic operations that we had pictorially at first. I drew everything, and people were reading Reddit or something. But just start paying attention now, because this is stuff that most of you probably need to get reacquainted with. Right. So here we are. These are the operations, and there are some now special. Maybe I'll highlight this for future reference. These are the basic operations. And now there are some very distinguished vectors that we care about, some special vectors. So the first type is the zero vector, 0. We usually just write as without the bar on top. And this is just the vector with 0 components everywhere. It's stupid, I know, but you need these for just technical reasons, all right? But there is something called a zero vector. It's different than 0, the number. 0, the number is just a point on the real line, or just 0 on the real line. A zero vector is slightly different. It's a vector with 0 in each component, right? If you're a computer programmer, this is of a different type, right? You have some type that's called integers, and there's a 0 there. There's a real type of float or whatever, that's 0. This is a specific class, right? It's a type. It's called a vector, and there's a 0 in this family. It's different than the other zeros, but interpret it as just a point. All right, it's 0. Slightly less dumb, but also probably more important, is the unit vector. I'll highlight this because it's slightly less dumb and actually useful. The unit vector is given any vector or any non-zero vector v. The unit vector in the direction v is v divided by its magnitude. This has components. You divide out by its magnitude, which is v1 squared plus v2 squared plus v3 squared. And this is a number c, for example. And so you just want to multiply this to v1, v2, v3. So visually, what is this? If I have a vector v, then the vector v divided by its length, it points in the same direction as v, but has magnitude 1, hence unit. All right. Exercise. Let v be equal to 1 minus 1, 2. What is the unit vector associated to this? Right. So this should be the square root of 1 plus 1 plus 4, not 0.5, root 6. So remember, when you want to find the magnitude of this, you're squaring each of these separately, and you're square rooting the result. So it's positive root 6. And so what is v over its magnitude? Well, then v over its magnitude is going to be 1 over root 6 minus 1 over root 6, 2 over root 6. Right? This seems like kind of a stupid exercise, but it's one of those trust me, it'll become useful cases. But maybe one way it's useful is, a lot of times, like I gave you the example before, like giving directions to people, or trying to find what a line is. It really doesn't matter how large the vector is. Okay, so in essence, the unit vector really just captures all the information directionally about a vector. Sometimes you don't really care what the magnitude, if it's not a force, you don't really care how strong the force is. You might just want to describe vaguely what the direction of something is, in which case the unit vector is a very nice way of doing so. It just tells you the direction, all right? And you assume the magnitude is 1. There are certain particular cases we'll get to soon where you're finding where it really does matter computationally that you just want the direction, but it's important that the magnitude of the direction is just 1, because it simplifies calculations that we'll do later, like with a dot product, which we'll get to. All right, so unit vectors come up a lot in calculations. So this is how you find them. Once again, as is the case with everything we've done so far, it works in any number of dimensions. All right, you just have to adjust the number of components here accordingly. Okay, so let's look at some actual more examples before everyone actually does fall into a coma. Let's do some application. Consider the following forces acting on a point. So let's say here's a point P. All right, now I'm going to put in coordinates here, x and y. And let's say I have a force that's pulling this way, F1, and this is making an angle of pi over 4. And I have another vector. Let's call this F2. And let's say F2 makes an angle of pi over 6 as drawn, okay? Let's say F1 has magnitude of, let's say, 100 newtons. F2 has magnitude of 150 newtons. And here are the questions. What is the, I should probably put arrows on top. These are all vectors, right? So F1, F2. What is the resultant force? I guess the net force. What is the net force on P in components? And B, what is the force, let's say G, that needs to act on P? So there is 0 net force. Okay, so a couple of things here. The first thing is to find, what is the resulting arrow F1, F2 of F1 plus F2 on this point. And the second one is, how do I cancel that out? And by the way, in this case, you should write this in component form, right? I'm not asking you to do the caveman drawings we did earlier on, but you got to actually put some numbers to this. So let's maybe this is a tall task right away. Let's say for A, the strategy ought to be, let's try and write everything in component form, right? So once we get the actual components of F1 and F2, then the addition subtraction becomes a lot easier. So write everything in components. Let's focus on F1 first. Does someone want to volunteer what the components of F1 are? So these are two-dimensional forces in this case, right? Because I've drawn them in 2 dimensions. Its magnitude and its angle in the angle it makes with a positive x direction at the very least, right? So AC has the right idea. You split it up in x and y component and sum it up, and then UMRF has the correct components. So here's how we do it, right? So once again, some trig involved. This is the hypotenuse of a certain triangle. Its length. The length of the hypotenuse is 100. Now, what's the x component of this? Think back to sort of polar coordinates, right? That's the intuition behind polar coordinates. How do I get the x component of a radial arm with length r 100? Well, it's 100 cosine pi over 4. What's the y component? Is 100 sine pi over 4. And remember from last time, pi over 4 is one of the special angles you really should know for this class. So this is going to be, it has components 100, which is the length of the hypotenuse, times cosine pi over 4, 100 sine pi over 4 for the y component. And we do this, this is going to be 100 over square root 2, because cosine pi over 4 is the same as sine pi over 4, which is 1 over root 2. And now F2, what should F2 be? So what's the x component? What's the x component of F2 here? So it's this way. It's nice if you have some pen and paper right now to draw the special triangles, but you want 150, right? You have 150 times the cosine of this angle. So what's cosine of pi over 6? Well, that's a 1, 2, root 3 triangle. So it should be 150. So let's see, 150 cosine pi over 6. And then you have, well, actually, let's leave this here for now. What's the y component here? What's the y component? Right, so it should be minus 150 sine pi over 6. All right, the minus sign is pretty important because you're not going, it's not a positive 150 sine pi over 6, because certainly, looking at the orientation of this arrow here, you're pointing somewhat downwards in the y direction. So it has to be, in terms of the direction up, which is pointing this way, it's minus. The tip of this arrow has coordinates that are minus in the negative in the y direction. It's minus 150 sine pi over 6. And now we have to, remember our triangles. So cosine of pi over 6 is going to be root 3 over 2, right? So it's 150 root 3 over 2. So it's 150, well, it's 75 times root 3. And then minus 150 sine pi over 6. Sine pi over 6 is 1/2. So that's going to be minus 75. Any questions? Okay, so the net force, that's going to be F1 plus F2, which is going to be 100 over root 2 plus 75 root 3, and then 100 over root 2 minus 75. There we have the net force, F1 plus F2. Now, what's the force that I need to make sure that there's no net force to this? Right, so you want G. So remember, part B of this is to find a force G that cancels out the net force. So you want G plus F1, F2 to be equal to 0. So what does this mean? This means that g must be equal to minus f1 plus f2, which is minus what I had earlier. Let's now try something a bit different, which is let's find unit vectors that give the direction of the tangent line to y is equal to x squared in R2 at the point, say 3, 9. Let me draw you the picture first. This is your standard parabola. We can draw a standard parabola. Right? So this is y is equal to x squared. There's going to be a certain point here that is sorry, the scaling is very off on this. Let me draw something better. There's a point, let's say here, say this is 3, this is 9, and there's going to be a tangent line to this, L. And I want to find the directions that correspond to this tangent line. So there's going to be a direction, well, two directions, one direction here, a negative of that direction, and I want to find that. So how might I go about this? Anyone with ideas on strategies on this? Okay, so if I take the derivative and plug in x equals 3, what does that get me? That gets me the slope, right, of this tangent line. And from slope, how might I get a direction? Remember, the slope is a number. So let's say, recall, L can be written in the form y is equal to mx plus b, where m is a slope. So let's suppose I have a line that's y equals mx plus b, and I know what the slope is. How might I get a direction off the slope? Given a slope, so we have several, let me go through the chat. We got something like 1/6. That might be right, I think. So we'll get to that soon. So slope is rise over run, which is y over x, which can be written as xy. Right, so in a sense, the slope tells you, right? What the slope tells you is if I go 1 unit in x, let's say if I increase x by 1 unit, then to stay on this line, I need to increase y by m units, right? Because, m times rise over run. So if the run is 1, then my rise is going to be m times that 1. So if then the direction, so it's not quite the unit, then the non-unit vector pointing in the same direction as L is either 1m, or what's the other option here? So 1m certainly gives me one direction. What's the opposite direction? Should be -1 minus m. Okay, so let's do the calculation. So m at the point 3, 9 is given by the derivative dy dx is equal to 2x, is going to be equal to 6. 2, the vectors, the non-unit vectors, are going to be equal to 1, 6, and minus 1, 6. I guess -1, -6. And what are the unit vectors in this case? What do I divide by? Right, so it's going to be root 37, 6 over root 37, or -1 over root 37, -6 over root 37. Okay, where did the 1 come from? So remember, the slope really doesn't, the slope is just a ratio of numbers, right? It gives you a number, it's not a vector. What I'm asking here for is you need to have, to get you the direction of this line, right? It has to be an arrow. I need to give you components. What I really have is a slope of this line. And what the slope tells you is if I move x units in the x direction, then I have to move y by m times x units. In other words, if I move 1 unit to the right, if I move 1 unit in x, 1, then to stay on this line, I have to move up m units. So in a sense, if I could have a direction vector where the tail is here, and I could have some x component of that direction vector. If the direction vector has x component 1, then I know for the arrow, the tip of my arrow of the vector to stay on this line, I must go up by m units in the y direction. All right, so that's how this works out.